The chemistry of epoxides is the chemistry of ring opening. This is a small, strained, three-membered ring, so it's not surprising that it opens readily. There are two types of reactions that happen during ring opening. One is reaction with nucleophiles without catalysis. The other is acid catalysis, promoting reactions with weaker nucleophiles. The results of these two ring opening reactions are different, so I'm going to talk about each separately. Take a look at the reaction when we treat with a straight nucleophile, no acid catalyst. You notice that it shows that this is done in protic solvent. Protic solvents provide a proton in the last step. There's quite a list of nucleophiles, and we'll add to it later, but take a look at the ones that we're talking about right now. Hydroxide, alkoxide, the sulfur cousins of these guys, cyanide, azide, and ammonia or amines. They lose H+, so they're equivalent of the NH2 or NRH anion. Quite a variety of functional groups that we can end up with. There are two special things about structural features of products that are worth noting, and will tell you that these products were made by ring opening of an epoxide. The first is that you'll see that there's a nucleophile on the carbon adjacent to a carbon that has an OH. So in every case, we have an OH on one carbon and a nucleophile on the next. That would be true in this other product as well. The second thing we need to point out is the stereochemistry of ring opening. If we number substituents on this epoxide, we'll see that 1 and 4 are back in the starting material, and 1 and 4 are always back in the product. 2 and 3 are toward us in the starting material and are toward us in the products. This fits our definition of stereospecific. The stereochemistry of the products is dictated by the stereochemistry of the reactants. And you see, like SN2 reaction, inversion occurs where the nucleophile adds. This would only be inversion at one carbon, the carbon that contains the carbon-oxygen bond in the reactant and the product must stay the same because that bond is never broken. But there's another question here. Where does the nucleophile add? Well, the nucleophile will add at both carbons unless there's differential alkyl substitution. If one carbon has more alkyl groups attached to it than the other, that controls the position of addition of the nucleophile. Take a look. You can see in this starting material I've added an R here so we know that this carbon is more substituted. It has more alkyl groups. And this carbon has fewer alkyl groups. Here it is over here and here. Under these conditions, when we see reactions like an SN2 reaction, you probably already guessed it. The nucleophile will add to the carbon that is less substituted. So you see in the product on the right, there are fewer alkyl groups where the nucleophile is added, more alkyl groups where the OH is. When we have differential alkyl substitution, the nucleophile prefers to add to the carbon that is less substituted. We call that regioselective when it selects one position over another. And it has the regioselectivity typical of an SN2 reaction. The nucleophile adds where there's less crowding, fewer alkyl groups. So in fact, we can say that this product is not formed. To summarize, when we have nucleophiles without acid catalysis, the reaction is regioselective, and the selectivity is like an SN2 reaction. The reaction is stereospecific, with inversion of configuration, just like an SN2 reaction. We'll preferentially form one product with the stereochemistry and the regiochemistry of the product that's shown on the right. Alternatively, nucleophiles can be added to epoxides with acid catalysis. Under these conditions, we use much weaker nucleophiles, and you're going to see a change in the regioselectivity. Take a look. The nucleophiles that can be used include water, alcohols, chloride, and bromide. With water and alcohols, we'll need a strong acid catalysis, such as sulfuric acid. For chloride and bromide nucleophiles, if we use the HCl and HBr, they bring their own acid with them. So these are the 4 nucleophiles we're speaking about adding under acid-catalyzed conditions. Again, as before, I've numbered the substituents on the epoxide so we can notice that this truly is a stereospecific reaction. In the reactant, we start with substituents 1 and 4 back behind the molecule away from us, and we end up with 1 and 4 in the product back away from us. And 2 and 3 are toward us, both in the reactants and in the products. So this is a stereospecific reaction, and again we observe inversion of configuration, just like an SN2 reaction. So keep that in mind. We see exactly the same stereochemical result as we did for the straight nucleophiles without acid. In both cases, they're stereospecific, and the reaction occurs with inversion of configuration, like an SN2 reaction. But how about the regiochemistry? How about the selectivity for addition of the nucleophile at one carbon compared to the other? Here we are with the reactant. The R group is added here to indicate that this carbon has more alkyl groups. And here it is in the product. And here it is in this product. Now I can tell you that the regiochemistry here is what you would predict from acid catalysis, where you had ring opening before the nucleophile adds. The carbon that has more alkyl groups is the carbon to which the nucleophile will add. This regioselectivity is just the opposite that we saw with the straight nucleophiles and no acid catalysis. Now it's this product that we don't see, and the product where the nucleophile has added to the carbon with more alkyl groups is preferentially formed. So we call this regioselective, but it's the opposite regioselectivity, and it's like the SN1 regioselectivity. So although the stereospecificity is like we see for SN2 reactions, the regioselectivity mirrors what we see for SN1 reactions. The nucleophile adds to the carbon that's more substituted. How good is that? By adjusting the conditions to be straight nucleophile or acid catalysis, we can control to which carbon the nucleophile adds, preferentially as we wish. So, ring opening reactions of epoxides. They're regioselective, they're stereospecific. And for those nucleophiles for which we can use acid catalysis, we can actually choose which carbon the nucleophile adds to. You'll see that this is very useful when it comes to organic synthesis.